What if dark matter never existed? Not in the way the question sounds. Not as a denial of observation. Not as a rejection of the mathematics that made it necessary. But as something more precise and in some ways more unsettling. What if dark matter was the right answer to the wrong question? This archive has reviewed the history of that hypothesis with the advantage of distance. And what that distance reveals is not a story of bad science. It is a story of good science operating at the edge of its own assumptions and not quite seeing the edge it was standing on. To understand how that happened, we have to go back to where it started. In the 1930s, a Swiss astronomer named Fritz Zwicky was studying the Coma Cluster, a dense collection of galaxies several hundred million light years from Earth. He applied a standard calculation, one that had worked reliably for smaller systems. He measured the velocities of galaxies within the cluster, and he calculated how much mass would be needed to gravitationally bind them together at those speeds. The number he got from the velocities and the number he got from the visible matter were not even close. The cluster appeared to contain far more gravitational influence than its light could account for. He called the missing component Dunkel Materie, dark matter. The term was vivid, it was useful, and it planted something in the conceptual soil of physics that would grow quietly and persistently for the next 90 years. In the 1970s, the hypothesis gained its most compelling evidence. An astronomer named Vera Rubin, working with Kent Ford, began measuring the rotation curves of spiral galaxies. The expectation, based on Newtonian mechanics applied to visible mass distributions, was straightforward. Stars near the outer edges of a galaxy, far from the concentrated mass at the center, should orbit more slowly, just as the outer planets of our solar system move more slowly than the inner ones. This is standard gravitational mechanics. It was not controversial. What Rubin and Ford observed was that the outer stars did not slow down. Galaxy after galaxy showed the same pattern. The rotation curves were flat. Stars at the periphery moved at roughly the same speed as stars closer to the center. This was not a small discrepancy. It was a structural failure of the prediction. Something was wrong, and the something appeared to be everywhere. The most natural explanation was that these galaxies contained far more mass than their visible components suggested. Mass that did not emit light. Mass that did not interact electromagnetically. Mass that was present only through its gravitational signature. Dark matter. By the 1980s, the hypothesis had moved from explanation to framework. Cosmological models were built on it. The large-scale structure of the universe, the way galaxies clustered and filaments formed, was simulated using dark matter as a necessary ingredient. The simulations matched observation with impressive accuracy. The case seemed closed, not by one piece of evidence, but by a converging structure of evidence from multiple directions. And yet, the particle was never found. This is a part of the history that, viewed from sufficient distance, carries particular weight. For decades, experiments were designed with extraordinary precision to detect dark matter particles directly. Underground detectors, shielded from cosmic rays, waited for a dark matter particle to collide with an atomic nucleus and leave a measurable trace. None came. Accelerators probed energy ranges where theorists predicted dark matter candidates should appear. They did not appear. Indirect detection experiments searched for the signatures of dark matter particles, annihilating each other in regions of high density. The signatures were ambiguous at best. Generation after generation of experiments returned the same answer. Either dark matter was not there, or it interacted with ordinary matter, so weakly that no instrument built from ordinary matter could catch it. The scientific community, to its credit, did not abandon the hypothesis lightly. Absence of detection is not the same as absence. A particle that barely interacts is genuinely difficult to find. The continued investment in detection experiments was rational given what the indirect evidence seemed to require. But something else was happening in parallel, and it deserves careful attention. Throughout the same decades that dark matter was being searched for underground, an alternative line of thinking was developing on the surface. In 1983, a physicist named Mordechai Milgram proposed what he called Modified Newtonian Dynamics, or MOND. The proposal was straightforward in concept, if unconventional in implication. Milgram noticed that the anomalous rotation curves appeared specifically in regions where gravitational acceleration fell below a certain threshold. Below that threshold, he suggested, gravity might not behave exactly as Newton described. A small modification to the law of gravity at very low accelerations could, he showed, reproduce the observed rotation curves without any additional mass. The response from the mainstream community was skeptical. MOND was treated as an interesting curiosity. It worked surprisingly well for individual galaxies. It predicted the relationship between a galaxy's luminosity and its rotation speed with an accuracy that troubled those who preferred dark matter models. But it struggled with galaxy clusters, where dark matter models performed better. It lacked a relativistic generalization for many years, and it sat outside the standard framework in a way that made many physicists instinctively cautious. There was also a sociological dimension worth acknowledging. By the 1980s and 1990s, dark matter had become load-bearing. Entire research programs depended on it. Graduate students built careers studying its properties. Funding structures, observational campaigns, and theoretical frameworks all assumed it. An alternative that eliminated the need for dark matter was not merely a competing hypothesis. It was, if correct, a structural disruption to an enormous amount of scientific infrastructure. This is not a criticism. It is a description of how large scientific communities function. The inertia of a successful framework is not intellectual cowardice. It is a reasonable response to the cost of being wrong about something foundational. But it does mean that alternatives tend to receive less attention, less funding, and less charitable interpretation of their successes than their track record might merit in a fully neutral environment. The question worth sitting with is this: what does it mean that two genuinely different explanations for the same set of observations existed, developed in parallel, and were never decisively resolved for more than 4 decades? It means the evidence was not as conclusive as the consensus suggested. This is not a comfortable statement, but it is an accurate one. The rotation curve data did not prove dark matter. It proved that standard gravity applied to visible matter made a wrong prediction. Dark matter was one solution. Modified gravity was another. The data required one of them or something else entirely, but it did not specify which. What gave dark matter its dominant position was not the rotation curves alone. It was a combination of multiple independent lines of evidence, including the cosmic microwave background, the large-scale structure of the universe, and gravitational lensing, all of which seemed to point in the same direction. This convergence was the real foundation of confidence. And yet, as the decades passed and the particle remained absent, a question began to surface in a growing number of papers, usually carefully framed, usually buried in conclusion sections. What if the convergence of evidence points not to an invisible substance, but to an incomplete theory of gravity? This reframing is subtle but profound. It does not deny the observations. It does not deny that something is missing from the standard picture. It asks whether what is missing is matter, or whether what is missing is a full understanding of how gravity behaves at all scales, in all environments, under all conditions. General relativity is our most successful theory of gravity. It has been tested with extraordinary precision in conditions ranging from the surface of the Earth to the orbits of binary pulsars. It predicts phenomena that were unknown when it was written, including gravitational waves, which were eventually detected a century after the theory was published. It is not a framework to be discarded lightly. But general relativity was developed and tested primarily in specific regimes: strong fields, solar system dynamics, compact objects, the cosmological scale, the specific regime of very low acceleration, spread across the diffuse outskirts of spiral galaxies, was not a regime the theory was engineered against. The assumption that the theory applied identically there, without modification, was reasonable. It was not proven. By the early 21st century, several theoretical physicists had developed relativistic extensions of modified gravity frameworks. These were not the crude patch proposed by Milgram decades earlier. They were genuine attempts to construct a complete theory of gravity that would reduce to general relativity in tested regimes, while behaving differently at very low accelerations. Some of these frameworks reproduced not just rotation curves, but a range of cosmological observations. They were not perfect, but neither were dark matter models, which by that point carried their own unresolved tensions. There was, for instance, the small-scale structure problem. Dark matter simulations predicted a specific distribution of small satellite galaxies around large hosts. Observations showed fewer satellites than predicted, and their distribution had properties the standard model struggled to explain. There was a core cusp problem, a discrepancy between the predicted density profiles of dark matter halos and what was actually observed at the centers of dwarf galaxies. These were not fatal flaws. They were addressed with increasingly refined models, but they accumulated. There was also a deeper issue, one that received relatively little public discussion. The properties of dark matter were constrained almost entirely by what the observations required rather than by any independent physical theory. Dark matter was, in a meaningful sense, defined by its unknowns. It did not interact electromagnetically. It did not interact via the strong nuclear force. It interacted gravitationally, and it interacted weakly in some models, though the weak interaction candidates never appeared in detectors. The hypothesis was structured in a way that made it both necessary and nearly impossible to falsify directly. Every failed detection could be accommodated by adjusting the assumed properties of particle. A hypothesis that can be adjusted indefinitely to accommodate negative results is not necessarily wrong, but occupies a particular philosophical position that deserves acknowledgement. It is doing the work of explanation without yet being subject to the discipline of refutation. This, where the epistemological layer of this analysis becomes essential. Science does not progress only through confirmation. It progresses through the structure of its falsifiability. A hypothesis that explains everything, because it can be tuned to explain everything, is not a scientific achievement. It is a placeholder, a well-motivated, mathematically sophisticated, extensively developed placeholder, but a placeholder nonetheless. Dark matter may be real. The particle may exist. It may simply require a new generation of instruments or a theoretical insight that reframes what to look for before it yields to detection. This archive does not claim certainty in either direction. The nature of this transmission is not to deliver verdicts, but to examine assumptions. What this archive does claim, on the basis of the historical record, is that the certainty with which dark matter was discussed in the early 21st century was not fully warranted by the evidence. The convergence of indirect evidence was real and significant. The absence of direct detection was equally real and equally significant. Both were true simultaneously, and the scientific community did not always hold them with equal weight. There is a reason for this asymmetry. The alternative was less developed, less simulated, less integrated into the broader framework of cosmology. MOND and its descendants could explain certain things well and other things poorly. Dark matter could explain other things well and those certain things poorly. In the absence of decisive tests, the better integrated framework won by default, not by evidence, by infrastructure. That distinction matters. Infrastructure is not evidence. It is accumulated investment in a particular interpretation. And when infrastructure becomes large enough, it begins to shape what counts as a problem worth solving, which anomalies are important enough to investigate, and which alternatives are worth funding. The history of this period shows a clear asymmetry in those decisions. None of this makes the scientists of that era wrong in their work. They were operating rationally within their constraints. They were using the best tools available. They were building on what had been established. But operating rationally within constraints is not the same as operating without constraints. And the constraints of 2026 were real, even when they were invisible to those inside them. The reframing that becomes possible from this vantage point is not that dark matter was a mistake. It is that dark matter may have been a category applied prematurely, an answer inserted before the question was fully formed. Gravity at the outer edges of galaxies was not behaving as expected. Something was accounting for that discrepancy. The decision to call that something matter rather than geometry, substance rather than structure, was a choice. A reasonable choice given the tools and concepts available. But a choice. The universe may contain dark matter. The universe may also contain gravity that is richer and more variable than the theories of 2025 described. These possibilities are not mutually exclusive. The eventual resolution may be that both were partially right, and that the real answer required a framework neither community had fully built. What this transmission invites you to notice is not the content of the debate, but its shape. Two explanations, both supported by some evidence, both challenged by other evidence. One dominant not because it was proven, but because it was integrated. The other marginalized not because it was refuted, but because it was isolated. This shape recurs throughout the history of science. It is not a failure. It is a feature of how inquiry works in communities with limited resources, limited time, and genuine uncertainty. But recognizing the shape makes it possible to ask better questions, to fund more diverse frameworks, to hold confidence more proportionally. The scientists who spent careers defending dark matter were not wrong to do so. They were doing the best available science with the best available tools inside the best available frameworks. Humanity was not foolish. It was early. Every field of inquiry goes through a period where the placeholder is mistaken for the answer, where the scaffold is mistaken for the building. The skill that eventually develops is learning to distinguish between them while still inside the structure. You are still inside this particular structure, which means something that feels certain to you right now, something that has indirect evidence, broad consensus, institutional investment, and a long track record of partial success might be doing the same thing that dark matter was doing, explaining enough to suppress the questions that would eventually replace it. That is not a reason for paralysis. It is a reason for proportionality, for holding the map loosely enough to notice when the terrain diverges from it, for keeping the alternative door open not because the alternative is right, but because the alternative being wrong should be proven, not assumed. The universe spent billions of years building structures that neither Newtonian gravity nor dark matter candidates fully described. Whatever is actually happening at the edges of those spiral arms, in the diffuse halos of mass that may or may not consist of invisible particles, the universe is indifferent to which theoretical framework humanity prefers. It will continue doing what it does, whether or not the instruments and concept exist to read it accurately. The question this archive leaves open is simple. When the history of this period is written from a position of greater knowledge, will dark matter appear as a discovery confirmed, as a hypothesis retired, as a partial truth embedded in a larger framework not yet assembled? From here, the answer is not yet something this transmission will deliver. What this transmission delivers is the question itself. Handed back to the time when it still mattered whether you asked it. Signal stable. Archive updated. Transmission paused.